Welcome to Class Connect Study Series with Yusuf Arikewuyo. In our last class, we examined instantaneous acceleration, and we said we can obtain the instantaneous acceleration from the differential of the instantaneous velocity. And of course, the instantaneous velocity is obtained from the differential of the displacement. That is, instantaneous acceleration can be written as the v dt or the square x dt square. That is the second differential of displacement with respect to time, or the differential of velocity with respect to time. Today we shall be considering motion under gravity. Motion under gravity, also called motion of free fall, is used to define any vertical, that is upward or downward motion, that can be influenced by the Earth's gravitational pull, that is gravity. Usually, a body can be projected to a height or can be made to descend from a height. These bodies moving from a height or towards a height are usually under the influence of gravity, and gravity is the force responsible for keeping all bodies under the Earth's influence in position. It can also be called the gravitational force. However, it is important to add at this point that not all bodies are under the influence of the Earth's gravitational pull. For a body to be unperturbed by the Earth's gravitational pull or influence, it must be given the escape velocity. And when we talk of the escape velocity, it is the minimum velocity that must be given to a body for it to escape the Earth's pull on it, or for it to disappear completely from the Earth's gravitational pull. For motion under gravity, there are some calculations also that are carried out. And these calculations are carried out using the equations of motion. However, we will try as much as possible to link the equations of motion to those equations used in motion under gravity. As a quick reminder, the following are the equations of motion. 1. S equals u plus v divided by 2 multiplied by t. We also have v equals u plus at. And thirdly, we have v square equals u square plus 2as. And lastly, we have s equals ut plus half at square. We shall modify these equations accordingly to suit the equations used in motion under gravity. The following changes are made to the equations of motion. To start with, alphabet changes. The acceleration a is replaced with acceleration due to gravity g in all the equations of motion containing a. That is, in all the equations, wherever we have an a, we shall replace with letter g, so that v equals u plus at becomes v equals u plus gt, because the a now changes to g. Also, v squared equals u squared plus 2as becomes v squared equals u squared plus 2gs. And lastly, s equals ut plus half at squared becomes s equals ut plus half gt squared. So we notice that all the a's in the equations of motion are now being replaced with g, that is acceleration due to gravity. Also, in alphabet change, the displacement s is replaced with the letter h to represent height in all equations containing s in the equations of motion, so that v squared equals u squared plus 2gs becomes v squared equals u squared plus 2gh. And also s equals ut plus half gt squared becomes h equals ut plus half gt squared, with all the s being transformed to h in this case. The second adjustment made to the equations of motion for motion under gravity is the sign change, and this has to do with if the body is moving upward or falling from a height. The first case we shall consider for sign change is the upward moving bodies. When a body moves upward, the body moves against the Earth's gravitational pull, and as such, the acceleration due to gravity g becomes negative in all the equations of motion containing g. For bodies moving upward, the acceleration due to gravity g is negative, and as such, the modifications for the equations of motion become 1. V equals u minus gt, then v squared equals u squared minus 2gh, and lastly we shall have h equals ut minus half gt squared. The g's, that is the acceleration due to gravity, is negative, indicating that the body is trying to move away from the gravitational influence or the gravitational pull of the earth. The second consideration for sign change has to do with bodies falling from a height or downward moving bodies. When a body falls from a height, the acceleration due to gravity g remains positive, and as such, the equations of motion remain the same. That is, v will be equal to u plus gt, v squared equals u squared plus 2gh, and lastly, h will be equal to ut plus half gt squared. The final modification for the equations of motion for motion under gravity considers the values of the initial as well as the final velocity. In the first instance, if a body falls from a height, the initial velocity, that is u, is 0, so that the equations of motions become v equals gt, h equals half gt squared, and lastly, v squared equals 2gh, since u equals 0 for bodies falling from a height. The second instance for consideration has to deal with the case when a body is thrown vertically upward. That is, in this case, the final velocity will be 0 at maximum height, so that the applicable equations of motion become 1. U equals gt, and lastly u squared equals 2gh when v equals 0 at maximum height. Thus, the equations of motion to be used for motion under gravity are as follows. 1. Let's consider the upward moving body. In this case, we shall have the following. 1. V equals u minus gt, v squared equals u squared minus 2gh, and lastly, h equals ut minus half gt squared. Now, this doesn't consider the fact that u becomes 0 or v becomes 0. This only gives the equation of motion to use. However, at maximum height in this instance, at maximum height, v becomes 0, so that the first equation of motion becomes u equals gt, the second becomes u squared equals 2gh, and the third one of course doesn't have v. Likewise, for bodies coming downward, the equations of motion to use are the following. We have v equals u plus gt, v squared equals u squared plus 2gh, and lastly h equals ut plus half gt squared. It should be added that the equation h equals ut plus half gt squared can be used to obtain the time it will take a body to fall from a height, that is from h equals ut plus half gt squared, and also knowing the fact that u equals 0 for bodies falling from a height, so that we shall have h equals half gt squared. To however obtain the time it will take the body to move from a height, we'll make t the subject of the formula, so that we shall have t squared equals 2h divided by g, And taking square root of both sides, we shall have T equals the square root of 2h divided by g. And this particular expression is worth it. It makes us understand that for bodies falling from a height, the time it takes to drop to the level ground is independent of their masses. That is, when we have a lighter mass and a heavy mass, as long as we ignore the influence of air, that is the air resistance, both bodies will land at the same time. However, if air is considered, the massive body will drop before the lighter mass. Thanks so much for watching. Hope to see you in our next class, and please do not forget to subscribe and click on the notification button. Thank you.